Good morning. My name is Riccardo Rasconi, and I will talk about a novel ant colony optimization algorithm that tackles the quantum circuit compilation problem. The outline of this talk will be quite linear. First, I will briefly describe the quantum circuit compilation problem, then I will move on to describing the details of the ant colony optimization algorithm, and finally, I will present the obtained results together with some possible lines of future work. Quantum algorithms are generally described in terms of quantum circuits. A quantum circuit is composed of a set of quantum states that are the values considered during the computation, a set of quantum gates that are applied to the quantum states and change their value, as well as a partial ordering relation among the quantum gates. In this work, we will consider quantum gates that are applied to one Q state, unary gates, or to two Q states, binary gates. In particular, we will focus on the compilation of quantum circuits that resolve instances of the max-cut problem, according to the quantum approximate optimization algorithm paradigm. As known, the max-cut problem revolves around finding the sets of vertices in a graph that maximize the number of cuts in the same graph. Quantum circuits that realize max-cut resolutions entail the presence of a quantum state for each vertex of the graph to be cut, as well as a number of binary phase shift gates for each edge, and a unary mix gate for each vertex. The circuit can be composed of multiple phases. There exist ordering constraints that must be satisfied among the quantum gates within each phase, as well as ordering constraints between quantum gates belonging to different phases. We will consider three quantum hardware architectures of increasing size, that is, composed of 8 qubits, 21 qubits, and 40 qubits, inspired by Rigetti technology. In the quantum architecture considered in this work, binary gates can be executed only if the involved quantum states rest on adjacent qubits. Therefore, compiling an ideal quantum circuit on a real quantum architecture basically entails properly adding swap gates to the circuit, thus moving the Q states across the quantum hardware and make them eventually adjacent to allow for binary gate execution. A swap gate exchanges the quantum states located in adjacent qubits. Just to provide an example, let us suppose that we have to execute a phase shift gate between the Q state Q3 and Q7. At the moment, this phase shift gate is not executable because Q state Q3 rests on qubit 3 and Q state Q7 rests on qubit 7, and they are not adjacent. So what we can do to address the situation is the following. We could swap the Q state 3 and 5 and the 7 and 8 at the same time. Therefore, putting the Q state 5, 3, and 7 adjacent, and now the phase shift between Q state Q3 and Q7 is now executable. To wrap up, compiling an ideal quantum circuit basically entails planning for and adding to the ideal circuit the proper number of swap gates in the proper position, as well as effectively scheduling all the phase shift and mix gates while respecting the ordering constraints among them. Very importantly, the compiled circuit must be as short as possible in order to minimize the decoherence problem that affect current quantum technology, which makes so that Q state values deteriorate with time. So the circuit must be executed as fast as possible. Starting from the paper Venturelli et al. 2017, where the authors introduced the benchmarks and attacked the compilation problem using temporal planners, there has been a number of works in the literature that tackle the same problem against the same benchmarks. In this work, we will focus on the results obtained in Chand et al. 2019, as they represent the current best at the time of our experimentation. In particular, we propose an ant colony optimization algorithm. Ant colony optimization algorithms basically simulate the behavior of a colony of ants, where each ant is a solver, and the ends indirectly communicate with each other using pheromone values. As the pseudocode shows, the algorithm lets all ends find a new solution at each optimization cycle until a termination criterion is met. At the end of each cycle, the pheromone values are updated, thus leading the ends towards more and more promising solutions. At the end, the best solution found is returned. The key procedure of the ant colony optimization is the BuildSolution procedure, which returns a feasible solution starting from an empty solution S at time t equal to 0. For each time t, the BuildSolution procedure selects a quantum gate to insert in the solution, either a phase shift, a mix, or a swap gate, until the solution is complete. The selection is performed by the SelectEligibleGate procedure, which picks up the quantum gate that, among all the eligible gates at time t, appears to be the most promising to obtain a good solution. A gate is eligible if it is supported, that is, if the ordering constraints of the gates preceding it in the solution are satisfied, and if the involved Q states are adjacent. If no operations can be selected at time t, time is increased to the value time plus 1. Basically, the SelectEligibleGate procedure starts by collecting all the eligible gates at time t. Subsequently, the heuristic value of all such eligible gates are computed according to a heuristic briefly described in the next slide. Then, a further pruning of the set of eligible gates is performed using a priority rule described later. Finally, the ant colony optimization probability is computed for all the gates in the pruned set, and one gate will be randomly selected for insertion in the solution according to such probabilities. The heuristic function mentioned in the previous slides is taken from the work Oddi and Rasconi 2018. It basically computes two values for each gate, dsum and dmean, and then returns a double key ranking of the gates based on such values, with dsum as primary key and dmean as secondary key. The dsum key associated to a gate is computed as the number of swaps needed to make adjacent the Q states of all the remaining supported phase shift gates besides the gate under analysis, while the dmean key is the minimum of all such values. The priority rule mentioned earlier is instead inspired by what has been proposed in Chand et al. 2019. It basically consists in returning the set of all eligible phase shift and mix gates together with the eligible swaps that improve the dsum key value. If no such swap exists, then we consider the swaps that at least do not worsen the dsum but do improve the dmean key value. In case no such swaps exist, we content ourselves by considering the swaps that improve the dmean value regardless of dsum. Subsequently, a selection probability value is computed for all the gates in the pruned set returned in the previous step. Such probability value depends on both the pheromone value, tau, and the desirability value, eta, associated to each gate. The desirability value, eta, of each gate is computed with the formula shown in the slide, which depends on the normalized values of dsum and dmean. Eta is itself a normalized value in the interval 0-1. As visible, the lower the dsum and dmean values, the higher the desirability associated to the gate. The pheromone model used in this work is the fuzzy time operation model. Given the basic pheromone model called time operation, in which the value associated to each gate depends on the time t of its insertion in the solution, the fuzzy time operation model considers the weighted average of the pheromone values of the gate computed at times spanning w time steps on the left and on the right of time t. The pheromone fuzzy operation model proved more performing than the basic time operation model, and this is why it is used in this work. Given the number of parameters involved in the algorithm, we had to execute a preliminary tuning phase using 15 new randomly generated instances, 5 for each value of n. As a result of the tuning phase, it was clear that the best pheromone model is the fuzzy time operation model, and that the best values for alpha and beta are 1 and 0 respectively. Recalling the ant colony optimization probabilistic formula, the fact that beta is equal to 0 means that the heuristic function does not seem to be helpful in the probabilistic choice of the gates. However, the same heuristic does play a very important role in pruning the gates before gate selection. As a matter of fact, preliminary versions of the ant colony optimization demonstrated that avoiding the heuristic-based pruning did not yield good experimentation results. I will now discuss the obtained results. As previously anticipated, we have compared our ant colony optimization with the rollout heuristic procedure of Chand et al. 2019. Our benchmark is composed of 50 instances for each quantum hardware chip. In all the experiments, the termination criterion is the execution time, limited to 60 seconds for the N8 qubit instances and 300 seconds for the N21 and N equal to 40 qubit instances. We have run the ant colony optimization 10 times for each instance, reporting the mean, the standard deviation, and the best results compared to the best result obtained in Chand et al. 2019. In the N equal to 8 case, we have improved 14 instances on over 50, obtained the same results in 18 instances, and we were outperformed in 18 instances. Moreover, the p-value of the Wilcoxon sign rank test on the ant colony optimization results against our counterpart was rather large, was around 0.2. So, the results obtained in the smaller instances do not seem to be very promising. Yet, we will see that things significantly improve in the largest instances. In fact, in the N equal to 21 case, we have improved 35 instances over 50, obtained the same results in 8 instances, and we were outperformed in 7 instances only. Moreover, the p-value of the Wilcoxon sign rank test was much smaller, proving the probabilistic significance of our results. But the best performances have been obtained in the N equal to 40 case, where we have improved all 50 instances. In addition, in almost all the instances, the average makespans obtained by the ant colony optimization were better than the best values obtained by the rollout heuristics of Chand et al. 2019. Again, the Wilcoxon sign rank test certified even more the validity of our results. To conclude, in this work, we have proposed an ant colony optimization algorithm for the resolution of the quantum circuit compilation problem, where the novel contribution is a new pheromone model which leverages a heuristic-based priority rule inspired by the priority rules proposed in recent literature. The experimental results obtained were very good compared with the best results in the literature, showing the scalability properties of our algorithm. In future work, we plan to test our algorithm against instances that take into account the initial state determination of the circuit as well as the crosstalk constraint. In addition, we plan to test our algorithm against graph coloring quantum instances instead of max cut. And lastly, we intend to further investigate the possibility to integrate local search in the current algorithm, given that normally ant colony optimization algorithms improve using local search. In this particular case, however, the utilization of local search moves is not easy, as given the highly interconnected structure of each solution, each local move is very likely to produce an infeasible solution that must be repaired. And this is all. Thank you for the attention.